Jay. So in the continuation of the series of lectures on electromagnetic field theory, now we will discuss about magnetostatics. So in the magnetostatics, there are two major laws governing magnetic fields, magnetostatic fields. First one is Biot-Savart law, and second one is Ampere-Circuital law. So, like electrostatics, there were two major laws, Gauss law and divergence law. So, like similarly, here two major laws governing the magnetostatic fields. There are Biot-Savart law and Ampere-Circuital law. So, one by one we will study both the laws. So, first one is Biot-Savart law. So, Biot-Savart law states that any current carrying conductor with the help of any current carrying conductor, we can find out the magnetic field intensity at any point P. So from the figure we can see here this is the current carrying conductor I, and its differential length is dl, and its at point P we have to calculate the magnetic field intensity H. So if we are taking the differential length element dl, so we can calculate dH, or differential magnetic field intensity. So we now connect this point to the differential element by making an angle alpha, and the distance of the point P to the differential element is r. So the Biot-Savart law states that the magnetic field is directly proportional to the I dot dl multiplied with angle sin alpha, that is the angle between the line joining the current element to the point P, where we are calculating the magnetic field intensity, and divided by the square of distance between them, the point P and the line joining of current element. So this is the dH. dH is the differential magnetic field intensity, or we are calculating for differential elements. So by integrating we can find out H equal to Ki, K is the proportionality constant, Ki dl sin alpha divided by r square. So where K is the constant of proportionality, its value is 1 upon 4 pi. So by putting the value of K in the equation of dH, we will get I dl sin alpha or sin theta divided by 4 pi r square. This is the general expression, and in terms of unit vector and coordinate system, we can introduce the unit vector along the r direction. So AR is a unit vector, that is the direction representing the direction of this, and divide by r square. So we can write dH equal to IDL multiplied with vector r divided by 4 pi r cube. So this is the Biot-Savart law. Next is Ampere-Circuital law. Ampere-Circuital law states that the line integral of the tangential component of H around any closed path is same as the net current I enclosed by that path. So mathematically we can write here the line integral of current carrying element IDL, that consists of magnetic field intensity H dl by circular integral, this representing the circular path, closed path. So the circular integral of H dot dl is equal to the current enclosed by that path is called Ampere-Circuital law. By applying Stokes theorem states that the line integral of any vector is equal to the surface integral of curl of that vector. So this is here we have taken H magnetic field intensity as a vector for Stokes theorem. H dot line integral of H dot dl equal to surface integral of curl of H vector. So this segment is the Stokes theorem, and by the Ampere-Circuital law statement, this is equal to I, current enclosed by that path. So if current is equal to H dot dl, so current will also be equal to the surface integral of del cross H. So here we can say that I enclosed equal to current density surface integral of current density. Del cross H can be written as equal to J. J is the current density, H is the magnetic field intensity. So the surface integral of del cross H equal to J, we can express here. So this is the point form, or this is the integral form of the Maxwell's third equation, or we can write here curl of H equal to J. To curl of H equal to J, J is the current density. This is a Maxwell's third equation, which means that the magnetostatic field is not conservative. It means that it not equal to 0. So J cannot be 0. The current density cannot be 0 when there is a circulation of magnetic field intensity. So it means there will always be some current value if there is a circulation of magnetic field in a current carrying conductor. Okay? So it cannot be a 0. So this is the integral form of Maxwell's third equation, and this is the point form or differential form of Maxwell's third equation. Now come to the magnetic flux density. Now we will get the Maxwell's fourth equation with this formula, Maxwell's flux density. Maxwell's flux density and magnetic field intensity both are related to magnetic permeability. So magnetic flux density is denoted by capital B, which is equal to mu naught H. So as we have known here that V equal to mu naught H. Mu naught has a value of 4 pi into 10 to the power minus 7 Henry per meter. That is magnetic permeability, or we can say permeability of free space. So the magnetic flux S can be defined as the magnetic flux S in Webers, or magnetic flux density is the Weber per square meter or Tesla. So magnetic flux through a surface can be defined as the surface integral of magnetic flux density, or we can say magnetic flux density per unit area. So that is flux passing through a flux. So mathematically we can get in the expression of magnetic flux like electric flux as discussed in Gauss law. Similarly in magnetostatics we have a magnetic flux in the field where magnetic flux density carry magnetic field intensity per unit area. So psi can be written as flux surface integral of B dot ds, where flux can be expressed in Tesla or Weber per unit. Webers or magnetic flux density in Webers per square meter. So for a total flux passing through a closed surface, magnetic field must be 0. So this shows the law of conservation of magnetic flux, or we can say the Gauss law for magnetostatic fields. So if magnetic flux passing through a closed surface should also be equal to 0, because the total entering flux through a closed surface should be equal to the total exit flux passing through that surface area. So that's why we can say it is conservative, or we can say the sum of all flux should be equal to 0. Mathematically we can write the circular integral of B dot ds equal to 0, or we can say the surface integral of magnetic flux density passing through a closed surface should always be 0. This is the law of conservation of magnetic flux, or we can say it is a Gauss law of magnetostatics. So this is the fourth equation of Maxwell's equation. By applying divergence theorem, so we know that the divergence theorem that the surface integral of any vector field is equal to the volume integral of divergence of that vector. So this here it is the expression of divergence theorem. So here we have taken magnetic flux density as a vector. So surface integral of B dot ds equal to divergence volume integral of divergence of magnetic flux density. So but in previous slide we have find out that the surface integral of B dot ds equal to 0. So we will put it over here equal to 0. So we can obtain that the divergence of B, divergence of magnetic flux density should always be 0. It is also 0. So this is the Maxwell's fourth equation in point form, and this is the Maxwell's fourth equation in integral form. So we can say this is the Maxwell's fourth equation in integral form, and this is the Maxwell's fourth equation in point form or differential form. Now we conclude all Maxwell's four equations as shown in the table here. So these two equations, first and third, are for electrostatics, and second and fourth are for derived from magnetostatics or magnetic fields. So first equation is del dot D, divergence of electric flux density is equal to volume charge density. This is the differential form or point form, or this is the integral form. We can write in any form. So we can write surface integral of D dot D is equal to volume rho v, volume charge density. So this is the Gauss law. So Gauss law states that the total flux passing through a closed surface is equal to the total volume charge density enclosed by that area. So this is the Gauss law for electrostatics. Third equation is the representing the conservativeness of electric field. That means the curl of E equal to 0. Okay. This is the line integral of E dot dl equal to 0. We can say that for any closed path, the electric field intensity for path A to B and B to A should be equal to 0. The sum of electric field intensity from a closed path equal to 0. So this is represents the line integral of E dot dl equal to 0, or we can say curl of E equal to 0. So this represents the conservativeness of electrostatic fields. So now come to the equation 2nd and 4th. These are the Maxwell's equations derived from magnetostatics. So equation 2 represents the divergence of magnetic flux density equal to 0. This shows the Gauss law for magnetostatics. We can say non-existence of magnetic monopole. That means the monopole can never be exist in a single pole. There should be always two poles, north and south pole. So it also says there is a non-existence of magnetic monopole, or we can say it is a Gauss law for magnetostatics. Magnetostatics, or we can say the surface integral of flux, magnetic flux density is equal to 0. It is the conservative magnetic flux density. Now come to the equation 4. Equation 4 says that it is the Ampere circuital law. The any current carrying element can be find out the magnetic field at any point P. So del cross H equal to J. J is the current density and H is the magnetic field intensity. So a line integral of H dot dl equal to surface integral of J, current density. It is the Ampere circuital law. So these are the 4 Maxwell's equations for static electromagnetic fields. So first and third equation are the Maxwell's equation coming from electrostatics, and equation 2 and 4 are the equations coming from the magnetostatics. So all are the remarks. Now come to the boundary conditions, magnetic boundary conditions. In the magnetic boundary conditions, we can have a boundary separating two mediums of different magnetic permeabilities. So consider medium 1 having magnetic permeability mu1 and magnetic medium 2 have permeability mu2. So by applying Gauss law, magnetic flux B dot ds equal to 0 and H dot dl equal to I in both the cases. So we can obtain for this rectangular path, this is the boundary. Delta H has tends to be 0, a very small area we have taken from vertical, and the delta W has been taken the width of rectangular path. So applying H dot dl, Ampere circuital law equal to I to the closed path from A to A. Means we have to start A to B, B to C, C to D, D to A. So we have A to B H dot dl, then B to C integrating H dot dl, C to D, D to A, which is equal to the current, total current enclosed by that path, that is Ampere circuital law. So the total current can be represented as J dot delta W, that means the current density over the width delta W. K is the surface current density normal to the path delta W. So here for rectangular element, J dot delta W can be written as H10 tangential component, delta W is width, normal component of H delta H by 2, this is delta H by 2, and this is delta H by 2. Plus H normal component of magnetic field intensity delta H by 2 and minus tangential component of H of width delta. So this has been taken for positive and this has been taken for negative. So this has been taken for positive and this has been taken as negative. So all 4 elements will be there, cancel out as a positive and negative. So and delta H tends to 0, it means it is very small height that crossing the boundary. So we can get J dot delta W equal to tangential component of H1 first medium minus tangential component of second medium into delta W. Delta W is, that is the width, small width, that is equal to 0. We cancel out to each other. So we can get the current density equal to tangential component minus first medium and tangential component to second medium. So this is the subtraction. In vector form we can write is the subtraction of tangential component of magnetic field intensity of first to second, and this is equal to current density normal to the area of this. This means that if this is the current carrying conductor, so the H can be find out to the normal to that area. So this can be represented by cross for inward, and this can be dotted for outward. So come to the next slide. Now we can get using V equal to mu H, magnetic flux density is related to magnetic field intensity by using this formula. So if we have this relation of H10, we can find out the relation of V10. So we have had H10(1) and H10(1), H10(2) can be written as V10(2) by mu2 and V tangential 1 by mu1. So we can get by using this relation magnetic flux density of tangential 1 component divided by first magnetic permeability minus V tangential 2 divided by mu2 equal to J. This means that it depends or it discontinues at boundaries, and it depends on different permeability materials. A special case we can say, if there is no current density, then it would be, if it is a free of current, if there is no current flowing in the elements, and then the tangential component of H will be the tangential component of second magnetic field. So the V equal to mu H, it will be the V tangential component 1 by mu1 H and minus V tan to mu2 equal to 0. So we can write tangential component of first and second magnetic flux density would be equal to mu1 upon mu2, or relative permeability of first medium to second medium. This is the case where no current is in the element. Now we will apply the V dot ds Gauss law for magnetostatics for this equation, for this condition. So this is the conservativeness of magnetic flux density equal to 0. So we will apply V dot ds equal to 0 for this, for top, bottom and lateral surface. So all this equal to 0. So we will put over here the 0, summation of all V dot ds. Considering the delta H height as tends to 0 for top and bottom surface, so we can get the magnitude of normal component of V is Vn1 and Vn2 for medium 1 and 2 respectively. The top surface, top integral of V dot ds equal to the top integral of Vn ds. This represents the direction, normal direction of magnetic flux density, which is equal to Vn1 and integral of ds of over the top integral, that is a delta S. Delta is a very differential surface, Vn1 ds. So again for bottom surface, similarly we will get minus Vn2 ds by integrating the V bottom normal component of magnetic flux density of medium 2. It is negative because we are considering that flux passing through a surface is entering through a second surface. So entering surface is taken as positive and leaving surface, leaving flux taken as negative. So that's why here it is negative at bottom side. So at lateral entry it is 0. At lateral V dot ds equal to 0. There is no flux at the lateral surface. So we can write here V dot ds equal to 0 here. This is the entering flux and this is the leaving flux. One is positive, one is negative, which is equal to 0. So we can write here over it here Vn thus normal component of first magnetic flux density is equal to the normal component of second medium's magnetic flux density. So this is the relation. It means the normal component of magnetic flux density is continuous at the boundary. It does not affect the whatever is the material has been taken at the above the boundary. So it is free from material. Now we know that V equal to mu H. So for medium 1 and 2, we can convert the H component of normal Hn1 and divided by Hn2 equal to mu2 by mu1, and we can write as over here mu relative permeability mu r2 divided by mu r1. Okay, by dividing this formula. This means the normal component of magnetic field intensity is discontinuous at the boundary. It does not change. H is not continuous at the boundary. The field strength in two mediums are inversely proportional to their relative permeabilities. This means that H1 divided by Hn2 equal to epsilon R2 divided by epsilon R1, because Hn1 epsilon R1 equal to Hn2 epsilon R2. So we can say that it is inversely proportional to the relative permeability at the medium. Okay, so that's all for the magnetostatic field. So we will discuss further in the next class. Thank you.